So, this lesson is called the reaction quotient. Q. Q is essentially the same setup. It has the same exact setup as K. K being the equilibrium expression. But there might be a situation when you are given a K value, and what they want you to do is they want you to prove whether the reaction is at equilibrium or whether it's approaching equilibrium by moving on the right side or moving on the left side. So in order for us to determine whether a reaction with new initial conditions, with new concentrations, will the reaction be moving to the right, left, or is it already at equilibrium? So what we do is that scientists made up this this variable Q, so that we could compare it to K. And depending on that comparison, we can judge whether the reaction is proceeding in a certain direction. So if that doesn't make sense, it should make sense soon. So in this slide, I know there's a lot. It says, by knowing K, we can predict the direction of a reaction. So if K is very large, then we know that it's going to, the reaction tends to lean to the right. There's something else I need to tell you. If K is super duper large, like, I don't know, like 10 to the 30 power, for example, then the reaction is most likely not going to be an equilibrium reaction anymore. It's most likely going to be a completion reaction, meaning that it's going to go all the way to the right side, meaning that all of the reactant is going to be consumed, and you're going to make product, and mostly all of it is going to be product, unless you have a limited reagent. So far we know that by knowing K, we can predict the direction. So if K is larger than 1, it tends to move to the right. If K is less than 1, it shifts to the left. We could calculate the concentration of the reactants and products if we know K. If we're missing one variable, we could figure it out using the other concentrations or the other data that's presented to us. But again, there might be a situation where the reaction, we don't really know if it's at equilibrium, and so we have to do some comparisons. And this comparison is done by calculating something called a reaction quotient, which is Q. It is what you get when you plug in the concentrations of the products and reactants at any given time. So again, we don't know whether the reaction is at equilibrium. We're just gonna we're gonna look at the concentrations. This is the concentration for reactants. This is the concentration for product. We don't know if it's at equilibrium. So what we do is we calculate Q, and we compare that to the actual equilibrium constant, and we compare them. So if Q is larger, or in this situation K is smaller than Q, then the reaction is going to shift to the left until the reaction establishes equilibrium. But if K happens to be larger than Q, and typically when K is large in general, it tends to move to the right, and then it's going to establish equilibrium. But if Q is equal to K, then we say that the reaction that we're analyzing is already at equilibrium. So it has already reached the end point. So to make sense out of this, here is an example. It says there's a reaction. You're forming hydroiodic acid. And it gives us a K value. So the K value at equilibrium, the the constant is 51, okay? And it says if you start with 0.2 moles of HI and 0.0 moles of that and 0.03 moles of that in a 2-liter container, which way will the reaction proceed? So what you do is you calculate Q in the same way that you calculate K. Here we already have K, but they want to know if under these conditions, under these concentrations, is the reaction at equilibrium or not. So when we plug everything into the expression, again, has to be moles per liter, so that's where all of these fractions come from. It's dividing by 2 liters. We get 1.3, which is significantly smaller than 51. So if Q is 1.3, K is 51, K is larger. So if we look here, K is larger, so the reaction is going to proceed to the right. So it says here, reaction proceeds to the right to achieve equilibrium. That's all it is. It's just Q and K. We're just comparing the two, and depending on which one's larger, it tells you whether the reaction moves to the right or moves to the left. That's all there is to this lesson. It's a very simple lesson. So here, here's another example. Hydrogen and iodide gas react together to form hydrogen iodide gas. The equation is there, it's the same equation, and it says that the equilibrium constant is 710, right? Which is 7.1 times 10 to the 2 at a certain temperature. If the current concentrations are that, so if we're analyzing a certain reaction and those are the concentrations we see, is the reaction already at equilibrium, or what direction will move in order to establish equilibrium? So what we are going to do is we're going to calculate Q. So again, here's my whiteboard. Let me bring it up. There it is. Okay. So what we're going to do here is we are going to set up our expression. Q is equal to HI to the second power over H2 and I2. And we're going to plug it in. So HI is 0.58 to the second power over H2, which is 0.81, and I2, which is 0.44. And when we solve for this, we get 0.944. So that's what Q is. So that's Q. K is that number right there. It's bigger. So K is bigger than Q. And anytime K is bigger than Q, it's going to shift to the right. So that means that under these conditions, the reaction is not at equilibrium. Instead, it's still shifting, and it's shifting towards the right. Okay, so that's how you do these type of problems. Let's see. I want you guys to try one. So let's see. You guys try this next one, and tell me what you get. Pause this. Go ahead and pause it, and then go ahead and play. Okay, so now that you did this, what you guys did, I'm assuming, is you, oops, ooh, that's not good. Hold on. There we go. Nope, still not it. There you go. Okay, so what you guys did is you converted the moles into molarity by dividing by the volume. So the concentration here, the concentration of SO2, you guys divided 0.035 divided by 5 liters, and you got 0.007. And then you calculate the concentration of SO2CO2, and you should have gotten 0.5 divided by 5 liters, which is 0.1 molarity. Boom, there's a dot. And we still need Cl2, which is 0.08 divided by 5 liters. And you get 0.016. Okay, so now you're going to plug the expression Q equals SO2 times Cl2 divided by SO2Cl2, and you plug in those numbers. So SO2 is that, Cl2 is 0.016, and SO, all of that, is 0.1, right? There's no powers, and when you solve this, you get 0.00112. Okay, 0.00112. And we know that this is the equilibrium constant, which is bigger. So K is bigger than Q. And anytime K is bigger, it's going to shift to the right. Okay, so this is our conclusion, and this is our evidence. K is larger than Q, and that's what you should have gotten. Okay. All right, now you guys try the last problem. Or, yeah, one more problem. You guys could do it. Okay, so go ahead and pause this and then press play. Okay. Alright, so now that you tried it, this is what you, ooh. Whoa, 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 whoa. Okay, there we go. So, come on. Come on, come on, come on, come on. Come on. Come on. Oh, whiteboard doesn't want to cooperate. Okay, there it is. Okay. Come on. You can do it. Okay. So, what you guys did is you wanted to find Q, and you guys recognize that water is not part of the equilibrium constant or Q, so you put NaCl, it's aqueous, HCl, NaOH, right? And the concentrations are given to you already, so that makes things easy. NaCl is 6 divided by hydrochloric, which is 3.2, and NaOH, which is 4.3, right? Very easy math. Q ends up being somewhere around here, so 0.436. K is equal to 0.5. So, because Q is very similar, very similar to K, we could make the assumption that the reaction is at equilibrium or very close to equilibrium. So the reason is because sometimes we shouldn't be rounding numbers to the very end, and so, you know, whenever it's really close, we just say that it is at equilibrium. So just keep that in mind. If it's very close, just assume that the reaction is already at equilibrium. Okay? Alright, and that's it.